Welcome to day 24 of 50 days of tutelage. In this class, I'll be talking about acid and base. Now, generally, if you mention acid around a random person, one of the first instincts is to run away because they feel like acid will do a lot of damage on them. But if you're a chemist or you're a chemistry student, you know you have to work with acid at some point or the other. So today, I'm going to teach you everything you need to know about acid and bases. So let's get right into it. So the first thing I'm going to be talking about is we have different definitions of acids. And then these definitions, they are given by different persons. So I'm going to be taking each of the definition one after the other. Now, the first one, which is the very, very common one, is what we call the Arrhenius definition. Arrhenius definition. I just hope this particular spelling of the name is correct. So this is Arrhenius definition of acid. And what did this guy, what did he define acid as? It says that acid, they are substances that produce hydroxonium ion. They are substances that produce hydroxonium ions when they are inside water. They are substances that produce hydroxonium ion when they are dissolved in water. So this is what this definition is talking about. It's saying that whenever you carry a substance, this is a substance, and then you dissolve it in water. Inside water, one of the ions that it will produce, the positive ion now that it will produce, is going to be hydroxonium ion. And this is the Arrhenius definition of acid. Any substance that dissolves in water to produce hydroxonium ion as its positive ion. Now, what exactly goes on with an acid? How does it produce this hydroxonium ion? So this is what happened. If you react, let's say you have HCl now is an acid. The first thing that happens is that HCl is going to dissociate into H plus and Cl minus. So there's that dissociation of into H plus and what? And Cl minus. However, because these ions are dissociated inside water, H plus, Cl minus, and you have H2O. So what's going to happen is that this is going to form what we call H3O plus. So you can see you have like 3 hydrogen and then you have what? 1 oxygen. So this is exactly what Arrhenius definition is talking about. Therefore, hydrogen ion in water is regarded to as H3O plus, which is known as the hydroxonium ion. So this is the definition of Arrhenius. However, that is not really like enough to define acids. There are other acids that don't behave like this. So we have 2 other definitions that we'll be considering. The second one is the Bronsted-Lowry. The second one is the Bronsted. I just hope I'm spelling these names correctly. Is the Bronsted-Lowry definition of acid. And what is the definition of this according to Bronsted-Lowry? Basically, what it says is that an acid is a proton donor. An acid is a proton donor. So anything that is giving out proton is called an acid. So hydrogen is actually proton. So another, we also call hydrogen proton. Why? Because it has just a proton number of 1. So we call hydrogen proton. So in other words, an acid is somebody who in a reaction would donate hydrogen. That is the Bronsted-Lowry definition. So you can see that it's actually kind of close to what Arrhenius said here. So Arrhenius says that whenever they dissolve in water, they produce what? Hydroxonium ion. And how do they do that? They do it through the H plus. And then Bronsted-Lowry says that they are also proton donor. So it's almost like similar to each other. But one definition that stands out and kind of like it accommodates every type of acid is this concept of Lewis. Lewis definition of acid. So there is the Lewis definition of acid. And what exactly did Lewis say that acids are? So Lewis says that acid is an electron pair acceptor. Acids, they are electron pair acceptors. They are electron pair acceptors. So I'm going to define some things here and I'm going to try to explain as much as I can because I will have to use the concept of hybridization to explain what is going on here, even though this class is not on hybridization. So, but I have to use the concept of hybridization to explain. So I'm going to try my best to not make it too much about hybridization. So let's see what it is about. You know, example of Lewis acid, by the way, is BF3. This is boron and this is fluorine. So they combine together, they form BF3. Now, on the surface level, this is actually forming a covalent bond. And what happened is that if you write the Lewis dot structure of boron, you have boron here. So you have 1, you have 2, and you have 3. So when you have fluorine, fluorine is in group 7. So therefore, it will always share 1 electron. And we have 3 of them. So you have fluorine, 1 is here, another fluorine is here, another fluorine is here, sharing 1 electron each with this guy. Of course, fluorine has other 7 electrons around it, apart from the one that it is sharing already. So with fluorine now, you have 8 electrons here. With this, you have 8 electrons here. With this, you have 8 electrons here. But when you look at boron, how many electrons do you have altogether? You have 1, you have 2, and you have 3. So that's 6 altogether. So 2 electrons, 1, 2, 3, 4, 5, 6. So 6 electrons around boron. So that implies that boron has not yet attained the octet structure. It is not yet complete, even though this sharing is taking place. So therefore, it has room to actually accept 2 more electrons. It has room to accept what? To accept 2 more electrons. So what is going to happen there is that that empty place allows BF3 to accept electron pair. It allows BF3 to accept what? Electron pair. So that is why Lewis says that acids are electron pair acceptor, and this special type of acid are called Lewis acid. Now, let's explain this from the point of view of hybridization. What usually happens is that before boron gets ready to form a bond with fluorine, something usually takes place, which is called hybridization. And this hybridization also, what precedes it is excitation. I'm going to show you everything now. So boron, the atomic number is 5. So you have something of this nature, 1s2, 2s2, and 2p1. So if you draw the energy level, so you have 1s, let me give room for that. So you have 1s, you have 2s, and then you have 2p, 2s, and you have 2p. So in this place, you have 2 electrons. In this place, you have 2 electrons. In this place, you have 1 electron in this place. But boron has to make use of its valence electron, everything in this situation, for its proper bonding. And how many electrons does it have in its valence? It has 3 electrons. It has 3 electrons because I've already explained this in the previous class. So you can check the playlist to talk about when I talk about chemical bonding and all of that, electronic configuration. I've explained all of those things. So I'm just applying them now. So in this case now, you have 3 electrons in its outermost shell because the highest energy level here, we have level 2. So therefore, we have 1, 2, 3. However, in this place, you have 2 of them, they are paired already. You can see when I describe it here, boron contributed 1, fluorine contributed 1, fluorine contributed 1, boron contributed 1. That's exactly how the bonds are formed. So every of these bonds, every of these covalent bonds, they are formed through the proper sharing of electrons. And each person donates 1 electron each to form a bond. So 1 electron from one person, 1 electron from another person, then a bond is formed. That is a covalent bond. So in this situation now, these two are already paired. When they are paired, there's no reason for them to be sharing anything with anybody again. So they just remain like that. So therefore, excitation needs to take place. So therefore, we have this. So instead of 2s to have 2, then there is excitation such that now you are going to have this. This is your 2s and this is 2p. So you're going to have this. 1 electron would have jumped from this place. It has excited, and 1 electron was initially here. So the one that jumped from this place will go here now. So there are 3 now. So each of these 3 now, they are not paired. They are not paired. They're just 1, 2, 3. They're just single electron like that. But that is the first case. This is the excitation phase. So excitation happens first. Then the second thing that happens now is hybridization. That will be the last phase before it now forms this particular bond with fluorine. So, and what happens in hybridization is that when orbitals come together to form what we call hybrid orbitals. So s orbital and p orbital will come together to form what we call hybrid orbital. Now we have only one s orbital here. When I mean one s, now I'm not saying that the one s, I'm talking about one, like as in counting. One s orbital is going to be donated here, and then two p orbitals. Two p orbitals are going to be donated here. That implies that we're going to form three of them. Like it's going to be three, and you have what we call three sp2 hybrid orbitals. How is that so? Because we only have one of s, so let's say s raised to power 1 here, and we have two of p, so we have p2, making it what? Making it three of them all together. So we have three sp2 hybridized orbital. And what will that orbital be? That orbital will be in this nature. So you have one electron, one electron, one electron. So this is okay. But however, what happened is that you have been able to, sandwich these two together. So this is px, this is py, and this is pz. But only two of the p's, that is the px and the py, you only use two of them with the s orbital. So therefore, what will happen is that this guy will be empty, and because this guy is empty, it is able to receive electron pair. It is able to receive electron pair. And that is why, from Lewis' definition, these acids like BF3 are regarded to as electron pair acceptor because of that valence orbital that they have, empty orbital that they possess that can receive what? Valence electron. I know this is not it is not I'm not teaching hybridization in this class, so I just use that to explain a little bit. If you want to check hybridization, just make sure you are following the class. We'll talk about hybridization in another class. I think I've spent a lot of time already on that. So let's move on. So now that we have given the three definitions of acids. We've given the Bronsted-Lowry, we've given the Arrhenius definition. Another example of this Lewis is also your aluminum chloride. Aluminum chloride is also a Lewis acid. So quickly, let's move on to strength of acids. We have what we call the strong acid and we have the weak acid. We have the strong acid, we have the weak acid. Now, strong versus weak. When is an acid said to be strong? An acid is said to be strong if it is fully dissociated in water. If it is fully what? Dissociated in water. That is, it is completely ionized in water. So you have HCl, fully dissociated, you have H plus and you have what? Cl minus. But if it is weak, it is only partly ionized. That implies that not everything will be fully dissociated in water. Just part of it will be dissociated in water. So therefore, you are going to have a kind of less concentration of these ions, like hydrogen ion and what? And chlorine ion. There's going to be less concentration of them inside the solution. But also, another thing that people also make mistake is that there is difference between a strong acid and a conc acid, a concentrated acid. Now, the concept of strong acid is about dissociation. How much of your hydrogen ion is dissociated in solution? Now, in the case of strong acid, it's about mixing with water. HCl plus water. Yes, both of them, like, they involve water. But this time around, we are looking at the amount of HCl that is inside water. So if, let's say, you put a certain amount of HCl, you put it in 100 dm cube of water. This same amount of HCl, you put it in, let's say, 200 dm cube of water. So what's going to happen is that HCl is going to be fully dissociated in these two cases. That is, the hydrogen ion will separate from the what? From the chlorine ion. They are going to be fully dissociated. However, what you notice here is that this HCl would have to swim in a lot of water, and therefore it kind of reduces its potency. It's more like sugar. If you add sugar to a small amount of water, the whole thing will taste very sweet. But if you increase the amount of water, what's going to happen is that it will taste as though there is no sugar inside that solution. So therefore, what we're talking about when we say concentration is how much of the acid is present in the solution. But when we talk about strong, being strong, the strength of the acid, we're talking about whether when it gets to water, will it dissociate into its respective ions in the solution. That's basically what the difference between strength and then concentration are about. So that is that about acid. I don't want to go too much into some extra details. Now, to bases now, to bases. We have bases. Generally, bases are actually they are either an oxide. So bases are generally oxides or they are hydroxides. That is, when you have metals formed with oxygen or when you have them formed with OH minus, then you form bases in this process. But that's a general definition. But we have what we call alkali. Alkali, they are like a kind of subset of bases. They are the one that they dissolve in water because there are some bases that don't dissolve in water. There are some bases that don't dissolve in water, but alkalis, they are those special ones that dissolve in water. But we mostly concentrate on the alkalis, those that dissolve in water. And so therefore, we have three definitions of bases as well, based on how we have explained earlier. We also have the Arrhenius definition for bases in this place. So the Arrhenius definition for bases also define that bases are substances that when they are dissolved in water, they give what? They give hydroxide ion. They give hydroxide ion. That is what Arrhenius define it as. So a base is any substance that what? That when they dissolve, they give what? Hydroxide ion. However, like I said already, what I just defined now would only satisfy for alkali because not all bases dissolve in what? Not all bases dissolve in water. Not all bases dissolve in water. So a general mode definition will be that a bases, they are substance that when they react with this guy, H3O plus or hydrogen ion, they produce what? They produce water. But that's also a flawed definition. Definition is not really perfect like that. It's not perfect. So we have Bronsted-Lowry. We also have Bronsted-Lowry definition. Earlier, we said acids are proton what? They are proton donor. So therefore, what will this guy be? Bases, they will be proton receiver. They will be proton receiver based on Bronsted-Lowry. So proton receivers. That will be bases based on Bronsted-Lowry definition. And that is why when they receive a proton or when they accept a proton, they produce water in the process. But that definition is also not complete as well. That is why we have the concept of Lewis bases as well. Lewis bases. And Lewis bases, we say earlier, we said acids are electron pair acceptor. Guess who is going to be donating the electron pair? It will be the bases. So, for example, your ammonia, NH3, is a Lewis base. And that is because if you look at nitrogen is in group 5. So you have something like this. 1, 2, so you have 1, 2, 3, 4, 5. And then when hydrogen comes around, hydrogen bonds with these, hydrogen bonds with these, hydrogen bonds with these. So you have a covalent bond there, a covalent bond there, a covalent bond there. So when you look at this now, there's an electron pair revolving around this place now. And this electron pair can now be donated to an acid. Don't forget, I've been able to establish earlier that acids, they have what? They have this thing called a free orbital, an empty orbital. And this empty orbital can take an electron pair. So therefore, bases, they have that electron pair and they donate it. So therefore, acids, according to Lewis, are electron pair receivers, electron pair acceptors. But bases are electron pair donors. They give out electron pair. So you can see the difference between them like that. So be able to identify what a Lewis base is and what a Lewis acid is as well. So that's the basic introduction to what acid and bases are. So the next thing I want to talk about now, I want to talk about pH. I want to talk about pH values. So this pH value is actually a way to measure the degree of acidity or alkalinity of a substance. So we have pH. pH is a way of measuring the degree of acidity or alkalinity of a substance. And to do this, what we actually measure is the concentration We measure the concentration of hydrozonium ion. We measure the concentration of hydrozonium ion to do this pH. But also, we actually can also measure the concentration of hydroxide ion as well, and that gives us the the pOH. So on a scale, there's a scale from 1 to 14. And then as this scale proceeds, you have number 2, 3, and on like that until you get to 13 and 14. As this scale goes on, if this is a pH scale, that is, you have measured a pH, and you begin to get values like 1, 2, 3, and so on, then as you are moving from left to right, you are moving from substance that is acidic, you are moving to substance that is what? Alkaline in nature. So therefore, any substance between 1 to 6, they will be acids. But when you get to 7, 7 are called, any substance with a pH of 7, such substance is a neutral substance. That is, it is neither acidic, neither is it what? Alkaline in nature. But when you begin to go from 8 to 13 to 14 and all of that, then you are talking about what? You are talking about alkaline substances. Alkaline substances. That's basically what the pH then is about. But here's one thing I want you to note. pH talks about the hydrozonium ion. Well, pOH talks about the hydroxide ion. So therefore, we said low pH means it is acidic. When we say low pH now, we mean less than 7. But what about low pOH? Low pOH actually means high pH, because the sum of pH value and pOH value will always be equal to 14. So if I have a low pH now, so let's do a little bit of calculation. If I have a low pH now, so let's say we have low pH, which is, let's say, 2 now. 2 plus pOH equals what? 14. According to what I've explained earlier, low pH means acidic. So therefore, pOH in this case will be 14 minus 2, which is 12. And so if you have this pOH of 12, it corresponds with the low pH of 2. So therefore, this substance is acidic. So you can see what I'm talking about now. If a substance is acidic, it has high pOH. If a substance is acidic, it will be what? High pOH. And then if it is basic, or if it is alkaline in nature, it's going to have high pH but low pOH. So take note of that. You don't have to be confused at all. Know that low pH means acidic. So therefore, if the substance will be acidic and you want to measure the pOH, then the pOH must be high. So low pH and high pOH, low pH and high pOH, they mean the same thing. Let me write it there. Low pH, high pOH, they mean the same thing. So that's it basically for pH. I know that there are calculations to this pH, but I'm not going to be able to cover that in this video. I'm going to cover that in some other videos. And that's basically the introduction to acid and base. Finally, there's a reaction between acid and base. So acid and base, they undergo a reaction called neutralization reaction, and they produce salt plus water. They produce salt plus water. For instance, a mineral acid H2SO4 plus NaOH. This guy will produce Na2SO4 plus H2O. This Na2SO4 is a salt. As you can see, it got its metal from the base, and it got this SO42 minus from the acid. So I'm going to be ending the class with this particular thing. If you have not subscribed to the channel, make sure you do so. Like and comment as well. I'll see you in the next one.